Thank you, everybody. So I would like to, first of all, thank you, Azal Nepal, for this organizing this wonderful event and giving me a chance to talk in this event. And the topic that I'm going to present is performance and scalability. So let's first start with my introduction. So about me, I started my the software development career around 10 years ago from a software company named Bikalpa. And then from there, I moved to Versend, currently known as Cotivity. And then about 6 years ago, I moved on to LogPoint, where I'm currently employed as an engineering manager. The language primarily I have developed or worked so far on this 10 years journey is primarily Java. But apart from Java, there are many other languages which, upon need basis, I've worked on. So let's recap on what we have worked on the session so far. So we have built our test automation, test quality, product, and everything that required for a software. We have raised some capital, but now when we have everything ready and we have set up our engineering practices as well, so when we go to the market, so that is where this topic of performance and scalability really hits us, because that's when we really get to know how the market is going to work. Maybe we expect few users, but maybe everybody rush in. And like our previous speaker mentioned, the pain of growth. That's exactly the point this slide is going to maintain. Because when we face these issues are going to either make you a huge billionaire company, or if you can't cope with the scale, then you might just crash out in the early stages itself. So let's see what these two different means, because interchangeably, they are quite used. Performance and scalability, they mean like more or less kind of similar, but they are slightly different. Categorizing what performance is in a simple terms, it's like expecting more from the same resources. It applies to humans as well. If you expect more from a single person itself, like you have a food chain and you have a single cook, but you expect like him to serve food for 5, and then you expect more for performance, you expect him to serve food for 10 people. But scalability is a bit different, where whenever the customer grows or your base grows, you add more resources. Like in the example mentioned, you add more cooks because you have to serve more people and keep everybody happy. So scalability is basically giving more resources to get more from them as well. So basically, this is what the definition wise. Performance is how well a software system works for the given timeline, for the given requirements and everything. Whereas scalability is how well it is able to handle the extra load or the sudden rise in the user or data or everything that may arise in the real scenarios. Because like every one of us mentioned, speaker, like data is growing. Even though like LogPoint itself is a company that primarily focuses on data, but the pain itself is the more data. Every day there is, previously it used to be gigabytes, now it's terabytes, and then it's petabytes. So data is always going to grow, and that is always going to be a problem, and we need to scale accordingly to handle those things. So when do we need to think about them? Like I mentioned, in the presentation itself as well, we have prepared like, first we make a working software and then only think about performance, because premature optimization is really not good, because if we focus on optimizing in the early stages, we might not have a working product at all, because our only focus will be on optimization, and the main business logic and other things, we would be keeping them apart. So first get a working product, and then only focus on the performance. However, scalability is a bit different. So based on what you are developing and what your target area is, if you need scalability, there are a few things that you need to consider while designing them as well, because it's not easy to scale a system if it's not built that way. Basis needs to be covered for a system to be scalable. So that's basically how and when do you think about those two items. Next one is, how do I know if I have a performance problem? So like I mentioned, either you get a customer feedback because your service outrage, those things happen, and then you get a headline, if you're a good company, that your system is crashing, then you need to fix this. So that might be a performance or scalability, but how do you differentiate them? Like it's mentioned, if it's not even working for a single user, then you definitely have a performance problem. But if it's working for a single or a limited user, then maybe that's a scalability problem. Even in our Nepalese market, like whenever we get SLC results, every site goes down. That's a scalability issue, not a performance issue, because that is not intended to handle that many amount of load at that given time. So that is scalability factor. On the normal circumstances, everything seems fine, but whenever something is increasing, our application or our product is not being able to scale. So that is scalability, and we need to think, because this is one of the more important factors, because if you want to grow, then maybe you can live without performance optimization, because you can compensate performance with scalability, but without scalability, there's no way you can grow. So there are a few approaches on how to handle those different things. So it's a textbook thing. For performance, there's a performance optimization things, where there are steps of procedures that you can follow to find the bottleneck, whether it's memory or anything. And for scaling itself, there are majorly two approaches. Either you go vertical by pouring more money, or you go horizontal to get the infinite, where you have to pour even more money for the resources and for development in the initial phase itself. So talking about focusing on performance itself, basically in an application, these are the 4 parameters that we need to optimize, mainly CPU, memory, I/O, and network. So basically an application is basically working on these 4 parameters, and if you have a performance problem, it basically lies within these 4 areas. Either if you're disk intensive, maybe you need to buy a new better disk, or maybe your code isn't written appropriately, so it's either consuming more memory by slowing the process, or not you optimizing the CPU itself. Back in the old days when Moore's law was in full swing, this was not such a big factor, because as Moore's law predicted, every 18 months the processing power is going to at least double, or something like at least 1.5 or double. So basically you have to wait out 18 months and then your application would magically run faster. But now we don't have that leverage, so we are only getting more cores, but not the processing power itself, so we have to focus on these factors as well. So among these are the basic steps, like I mentioned, for analyzing the performance of any application. First of all, you have to know what that application is, what it's intended to do, because without knowing what you are profiling, you may not know, even if somebody is presenting like this is the bottleneck, you might not realize that this is the problem what you need to solve. So the first step is know your application, and then the second step is, once you have an idea of what your application is intended to do, how it gets data, how it processes, then you need to profile. And basically, like I mentioned, there are different tools. Some are mentioned here, like cache grind, val grind, flame grabs, heap dump, etc., for different purposes, like for memory profiling, for CPU, for disk I/O. More of those will be covered by the profiling application itself. And once you have the profile report itself, you need to know how to analyze that report as well. Because if you don't know how to analyze the report, the profiling, the basic sense of what the profiler is giving, you might not understand what it is giving itself. So you need to work on how to analyze the report as well, and then re-verify, because try, fail, that's for unit tests. But for performance in itself as well, you have to apply changes and see whether it's worth it, or whether it's really giving you the performance that you intended or not. And then re-look the whole process again and again until you find the real bottleneck. So let's go through a simple example of a CPU optimization problem. So let's say this is one of our requirements where we had to check for a string whether it's an IP or not. So there are basically numerous options on how we can find whether anything given as an input to a string is an IP or not. So this is basically a simple function, just around 6 lines, where we define a regular expression and then match the string to find out whether it's an IP or not. So if you have an experience, it's basically in Java itself. So if you have more experience in development itself, maybe you can find where the problem is in the code itself just by looking. But imagine this function is not just a simple function program, but it's hidden in 1,000 lines or maybe 10,000 lines of code. You may not be able to find the obvious mistake itself. So then how do we move forward? Like profiling this function itself currently yields around 244K iteration per second. So maybe that's good enough for now, but how do we know whether it's a problem or not? That's another step. So let's say we have this function, and suddenly a new scenario arises, or maybe the log volume or the data volume increases, and this 244K iteration per second, which was good enough for the earlier stages, is now not good enough. So people are complaining you are not processing the reports in the given time, or you are taking too long to process anything. So how do we move forward? So let's say of all the tools mentioned, so imagine there was a tool, maybe some magical tool which would profile application and it just takes few minutes and just point to like, here, where is you should handle things. So imagine that. So there are different tools, and among these tools, from a personal experience itself, we have been using a tool called Flame Graph. It's not coming. Just sliding board did क्या case करते Okay. So this is example of what a typical tool that we are currently using, Flame Graph, looks like. This was developed by Brendan Rogers, and it's basically a graphical representation of a stack trace. So that's exactly a flame graph for this previous application, where we can see the width of the application defines the maximum time where our application is spending time. So if you look at the flame graph itself, it's obvious where our performance bottleneck is. It's in the pattern matching, which we are doing for every iteration of that function call itself. So just spending a few minutes, if something gives you this much information, I think that's very helpful in optimizing the application of the process itself. This we have been using in our company itself, in different applications, and using these tools, we have been able to get around, let's say, 3 or 4 factors of improvement in many of our applications. So it's something really fascinating. So let's apply the performance that we just find out. So we just move the simple line of pattern compiling from the function to a static and then call the function. Now we get around 1.6 million iterations per second. So just by simple profiling, we got around 6 times of improvement. So it was an obvious case, but imagine, like I mentioned, this function might have been hidden in a 10,000 line of code block, and we would have never found it if we did not profile our application. So whenever we have something, we should research on tools itself, because that's more important. And once we have got the right tools, finding might be a much more easier solution when we know how to profile and analyze all the reports that are presented itself. Now, scalability. So like I mentioned, if we don't have any users, we're not going to have any scalability problems. So when scalability is really the actual pain of growth itself, because the more users log into our application or want to use our application, the more problem we'll be hitting, because that's where we need to grow as well. Like previous speakers mentioned, the whole engineering team needs to be more scaling out, the high burst factor. So that applies to all the software as well, because if a block is not going to work well, or if that has dependency with every other thing, we won't be able to scale things. So those things have to be designed and well thought of before we develop applications that are targeted to a wider audience. So these are a few of the scalability design guidelines that focuses, like that are the basis where we can build a scalable system on. One is architect upfront. So if your application is required to be targeted for a huge number of customers, so maybe you're using some news sites or some other weather portals where you guess or believe that a huge number of people are going to use your service, then you need to architect as well, because like I mentioned, it's not a performance problem. Scalability has to be from the base up. Otherwise, what we would be doing is we would need to re-architect the whole application itself, which The developers obviously like re-architecting their application, but that has a use cost itself and is not beneficial to the company. Apart from that, another thing is language choice. So language choice in a sense like if there are better languages for your suit needs, because there are languages which each language has its own advantage points and other things, like let's say Python has its own advantage for data analysis and other thing. But if we were to use Python for a really scalable system itself, we might have to be reinventing a lot of the Python itself. So if we choose a better tool which has, because let's say if we were to do in a much more easier language like Java or other thing, then we would be able to use more cores and more other things much simpler than in Python. But if you go through Python, then we'll have to spend a lot of budget in the language itself, because there are, as it's not a compiled language, it would bound to be slow, and we'll have to work on a lot of things by writing either foreign interfaces, like in low-level bindings in C, or maybe Rust, and that would take a lot more time for us. And another thing, the major part of the scalability is share nothing or share at least as possible, because in computer system, the main thing that spoils everything is state. If we were to reduce state from all of the designs, maybe our 90% bugs won't be there, because state is definitely causing issues everywhere. And another thing is separation of concerns. That basically goes for the microservices architecture. If you have a block doing only a single thing, then you can scale those blocks as well, separately develop and modify those blocks. Whatever you want to do, you can do on that separate block as well, as long as they have separation of concern design implemented. And another one is caching. So for performance also it's valid, and for scalable thing, it should be at least distributed caching, because centralized caching, you wouldn't want to implement centralized caching, as caching it itself might be a bottleneck when you do that in a scalable system. So imagine this for the scalable system. We want to create a new site, and we are expecting at least, let's say, 1,000 users, concurrent users as start, and our budget and our engineering team is designed that way. But something clicks, and everybody wants to view our site, and then we have 2,000 concurrent users. So even though it's a good thing, but it's a bad thing for the engineering, because we are not prepared to handle those 2,000 concurrent users in the first phase of deployment itself. So how do we handle that? That's where scalability comes in. And basically, like I mentioned, there are two approaches for scaling. One is scaling up, and one is scaling side. For the given limit time and other things, scaling up would be an easier solution, vertical scaling as they mention it, because more or less practically, if you have a good working solution of things, maybe you don't need to change anything. So this is where the Moore's law was helping us. Faster cores and other things, faster memory, faster disk, everything provided would basically scaling up the high number of requests per second itself. So we need not to worry, we just have to spend a few bucks and buy a new hardware. That would be better for us. And another one is concurrency. So like I mentioned, if we had implemented in some system like Node.js or Python, where consuming all the available cores is not straightforward, so we'll have to work on that. Otherwise, if we were to pre-design in a language that was concurrency away, maybe in Go or Java, then that would have been a least problem for us. And another scalability like vertical scaling. So just to handle 2K users, the simple solution is just spend few more money, and then that should handle for the 2,000 users, at least for current. But what if the current we scaled up and then the user base grew to 30,000 or 40,000? Then vertical scaling would not be a good solution, because that would be hugely expensive, and there's a limit up to where only we can vertical scale, because that's the hardware limit that we are going to hit. So these are the pros and cons of the vertical scaling, because like I mentioned, it's very easy. You just have to spend money and then buy hardware, so vertical scaling would more or less work with you. And if you are using a licensing product itself, maybe SQL Server or some other things, then less licensing cost, because you only have a single-use server, and less power consumption. And the cons are it's expensive. It's easier, cheaper buying 2 machines with low configuration than a single machine with very high configuration. And then as there's on a single point of failure, so it's very risky. If that goes down, the whole application may go down itself. And another one is horizontal scaling best practices. So like I mentioned, it's very tricky and very complicated to implement this and get this right, because its basic moral is it's designed to fail, and it's also designed to recover that from that failure, because just to apply the same logic and maybe using sharding or maybe MapReduce, or by using the microservices where we are making a big system by very smaller, integrating very smaller system, even a single smaller system failure should not be cause the failure of the whole system itself. So we have to work on availability, replicability, and fault tolerance for all the application in this mode. And this is very expensive, and this is where your company makes or breaks in the big time, because if you want to grow, this is very much indispensable for the growth. And another thing that could be applied for this scalability is asynchronous mode, because as you grow asynchronous, there's less dependency on different modules. And less dependency means we can scale individually these components and focus on the small target areas. So these are basically the pros and cons of this horizontal scaling. Like the pros, it's very cheaper because machines are cheaper, hardware is getting cheaper, and low-level machines are very cheap. And fault tolerance can be gained much easier by this thing because there are more machines. There is no single point of failure. And it can literally scale infinitely. Obviously, there are hardware limits and other things, but it can scale. And the cons is it's very difficult to implement, and you have to spend a huge budget at the initial stage to achieve the scalability. And other thing is licensing and more utility cost. So that's all from us. Thank you.